At now is the carbon nucleophile and how it can react. We saw super strong carbon nucleophiles in the Grignard and in the Wittig. Now what we're doing is scaling back down a little bit to a weaker carbon nucleophile in our enolates. We can make those enolates because we have that acidic hydrogen. Okay, why was that hydrogen acidic? Because there's resonance for the conjugate base, which stabilizes that intermediate, which is why we can remove that hydrogen. That now generates a negative carbon. Okay? So someone probably went through and set this up and said, okay, I want this carbon nucleophile, and now I'll go attack an electrophile, and they threw in some random electrophile. They noticed their yield was really piss poor. They said, okay, why is my yield so bad? So they went through and started to analyze everything that they obtained, and what they noted at the end of it was they ended up with this really odd product. If I could draw it right. Let's try that again. Yeah, I can do it that way. They ended up with this really odd product chilling in there, and they didn't really know what was going on with it. Said, okay, well, where did that come from? Okay. And if we look really, really carefully, where did it come from? It's 2 of the starting aldehyde. Okay, so it ended up reacting with itself somehow. Well, what is that somehow? We have a nucleophilic carbon in our enolate. And what else do we have? We also have an electrophilic carbon. It is that electrophilic carbon that actually stabilizes the enolate. But if I keep doing that. There's another video of me biting my tongue. That hurt. If we bring in a second molecule, we also have that electrophilic carbon on the other side. So if that goes through and attacks, we can break open the pi bond, and we've now linked those two to each other. Okay. Everybody see the pieces? So we had our red electrons and our blue carbonyl, just to tie that up. There is our red electrons are now in a bond, and our blue lone pair electrons are now up on that oxygen. There's another electron pair there. Make sense? Okay. What happens now? Is this structure stable? No, because it has charge. Okay. The simple way to fix that would be to go ahead and add hydrogen and do it as a hydrogen or an acid workup. Okay. We don't even need to get to the acid workup. We can actually pull hydrogen from our solvent, ethanol. Depending on how the reaction is shown, they may sometimes show that solvent, they may not. If we have sodium methoxide, we have ethanol. Okay? It is there by nature. Okay? And that comes from how we go through and make that. We would add something like sodium metal, which would react to form hydrogen gas and sodium methoxide. The hydrogen gas bubbles out, and we're still left with either our protic solvent and our strong nucleophile. Okay? So we can have a hydrogen come in, pick that up, we'd reform our ethoxide, and we'd have our protonated state for our final product. Okay? This is called the aldol synthesis because of the origins of this. Okay? If we take a look at our final product, we have the aldehyde functional group, and we have an alcohol functional group. They aren't directly tied to each other, but they're close enough and consistent enough in this process that we refer to it as the aldol. Ald for the aldehyde, and the alcohol for that remaining piece. Okay? If we take a notice, there are 2 more boxes shaded there that should not have been shaded, but, hints get given. What else might happen? And there's a reason I erased earlier ago. I said there was a product that was formed. That product that was formed, is that the aldol that's shown? This is where you could look at your notes and yeah, you'd be like, no, that's not what you drew up. You drew something else up. Okay? So something else is going to happen here. So let's take a look at what we have active in solution. Okay? We have the aldol and we still have ethoxide floating around. Okay? What reactive things do you see in there? What's that? We do have the pi bond out here, presumably. Okay. We could go through and form an acetal, or technically a hemiacetal, under the basic conditions. But remember, our acetals are not particularly stable unless they're cyclic. So it's not a bad idea, unfortunately, that goes in kind of a dead end that takes us back to the carbonyl. Okay. Remember, the whole thing started because we had an acidic hydrogen. Okay. Being alpha to the carbonyl. Do I still have alpha hydrogens? Yes. Are those hydrogens more or less acidic than the starting material? Why are they more? There's resonance in the first one, so I don't accept resonance as an answer. We have a second oxygen. We have an inductive effect of that oxygen withdrawing electrons. Those hydrogens are actually more acidic than we started. Okay? Which means I could remove one of them and put a lone pair of electrons there. Okay, well, so what? What does that do for us? Okay, what do you mean it forms a pi bond? Whoa, that was the wrong. Right, we could form a pi bond. Well, the other way would exceed the octet on that carbon. The OH would leave. Why do you not want the OH to leave, Wyatt? It sounded like you were not liking that idea. What's that? What solution am I in? Ethanol with a negative oxygen. So I have hydroxide, another negative oxygen coming out of solution. Negative oxygen in a solution that already contains negative oxygen. Which one's more stable? They're roughly the same. There isn't really a favoring one way or another. We're used to saying hydroxide is a bad leaving group. It is, because we're usually seeing hydroxide going into a water environment or an acidic environment. And in that case, hydroxide is a bad leaving group. Okay? It's going into an environment that is basic. Okay? So as a leaving group, it is roughly equally as stable as the solution around it. Okay? That in and of itself doesn't fix the problem, though. Now there's no favoring to continue forwards. Okay? So even if we say it's not that bad, it's still not good. It's not going to want to leave. Okay? Does it happen? Those people in lab should be, absolutely it happens, because that mechanism is exactly what you did in lab. You're like, wait, what lab was that? That was the exact step in the epoxide. We end up forming the double bond, kicking out the hydroxide leaving group. Okay? So we know it happens. So there has to be something else that we're missing behind this. Whoops. So if we draw out our steps, we would end up with that as our final product. Okay? And I don't think there's anything useful in that statement anyway, but we'll come back to it in a second. And the hydroxide. So I'm still with Wyatt on this. Hydroxide is not a good leaving group. Okay? Yes, it's not horrible, so this could happen. But at best, what I'm expecting there is a strong equilibrium between those two, not getting me a lot of product. And yet when we look at the product, we get almost exclusively that structure. What else am I missing?
Resonance.
What do you mean?
The pi bond can move, and
What pi bond?
the alkene one.
The alkene has resonance with the rest of the structure. There's now more resonance for those electrons, making that product more stable than any of the previous structures. Yes, it is reversible, but it is reversible to a very small extent. There's a large favoring for the aldol product due to the conjugation of those pi bonds. Conjugation, ultimately resonance, is what drives this reaction forwards. Kind of make sense? Okay, so let's clear that. The aldol reaction itself was really just this first part. That was the aldol. Okay, because we ended with an aldehyde and an alcohol. What did we do in the last step? We got rid of the alcohol. So we lost OH. We formed a pi bond. What kind of reaction did we do? An elimination. What did we eliminate? Hydroxide, which acts as a... fair enough, it does act as a leaving group in this case. I'm fishing for an N word. We're looking at a nucleophilic elimination, or a nucleophile elimination. Okay. That nucleophile elimination gets us that double bond. Okay. Effectively, what have we lost from this? So not only did we lose OH, but we also lost NH, right? So we formed a pi bond, loss of OH and H. What is OH and H combined? Water. So if I ran this reaction, I'm probably running it with a little bit of heat. What is going to happen to that water? It's going to turn into a gas that would then condense on our glassware, and we would see condensation. This reaction, beginning to end, is typically known as an aldol condensation reaction. It's the combination of both of those. It's the aldol followed by that nucleophilic elimination, which is really a fancy way of saying less or more specifically a condensation. Okay? So when we're running the aldol, typically it follows a condensation as well. Okay? We typically don't run just the aldol. Okay? The aldol on its own, relatively low yielding. Once we follow it up with the condensation, we get a much higher yield because of that conjugation of the pi bonds. Kind of make sense? Okay. Because that makes so much sense, I think you should just do practice. Okay, so I added the hint with the stars and then the what, the WTF, and then the what the, as kind of hints as to different levels of difficulty among those. And then the stars should be sort of straightforward. Okay, you have the context to be able to answer those pretty well. You just need the practice. Okay, so I'm going to start in the upper right-hand corner. Also screwed that up today. I want to take a look at that product. Okay, I have a strong base. Okay, so that strong base needs to find an acidic hydrogen. The acidic hydrogens we've been talking about would be the alpha hydrogen. So alpha to a carbonyl. So where's my carbonyl? There's my carbonyl. The alpha position would be a hydrogen connected at either of those red dots. Do I have a hydrogen connected to either of those red dots? No. I have a hydrogen that is that red dot. That's not an alpha hydrogen. That is a zero hydrogen. Okay? That hydrogen is not acidic on the aldehyde. Okay, no resonance to stabilize that. There's nothing there. If we look at the other red dot, that one could have a hydrogen or has the potential to have one, but it already has its octet, which means there's no hydrogen. So I've added base to a neutral species. What happens? Nothing. Nothing happens. The product that you get is no reaction. Okay. So let's take a look at the upper left this time. Okay? We've got that strong base. I need to find an acidic hydrogen. My acidic positions are at the alpha positions. Again, I have that aldehyde, not acidic. I only have that one purple spot that I've got. There are 3 bonds shown, which means there is an implied hydrogen. I do have an alpha hydrogen, which means I can make that nucleophilic, and I can initiate my reaction. Okay? There are going to be shortcuts on how we put these 2 structures together. Okay, so let's attempt one of those. I'm going to go through and show the ring. There's my carbonyl, and I actually want to twist that ring a little bit. Should probably draw the right number of carbons. Because that's my nucleophilic carbon, right? That red one. Okay. I want that nucleophilic carbon to attack my electrophilic carbon of my carbonyl, right? So there's my former carbonyl. My carbonyl, right? So I'm going to get rid of one of those pi bonds, or a pi bond, make that a negative. So there's that new link. That blue carbon is now connected out to whoops, now we got to make sure we do this right. That blue carbon is the purple dot in our starting material. There's a hydrogen. Nope. Let's fix that. Sorry. So where it's important to be careful with your carbons. There's our blue carbon. There's our dot. It's connected to a hydrogen, and then it's connected to that ring. Everybody see that? Okay. We'd have a negatively charged structure, which means it's not neutral, which means it's not done. Where do we get a hydrogen from? Ethanol in solution. We can attach the hydrogen onto that oxygen, and we'd have that structure. And what we now have is the aldol. Okay, our aldehyde in purple and the alcohol in blue. So far, so good? Remember, what we just talked about was that when we run the alcohol, or aldol, it very rarely forms just the aldol. It very typically does a condensation afterwards. To do a condensation reaction, that is an elimination. And in an elimination, what happens? We have a leaving group. That's our OH, which you said was the bad one. What else? We form the pi bond by the leaving group leaving and the removal of an acidic hydrogen. The acidic hydrogen would be our alpha hydrogen. Okay? Do we have any alpha hydrogens? We'd be looking at that red dot. Is there an alpha hydrogen there? No. Do I have all of the conditions to do the condensation? No. What happens? It stops here. We get just the aldol product. So when we're doing our aldol reactions, it is very common to just get in the habit of always throwing in the condensation. Okay? Probably 80% of the time you'll be right. Right? To just go all the way through with the condensation. Okay? But there's that probably 10 to 20% of the time where we're going to throw in something weird and say you can't just do the condensation. So watch out for that. To do the full aldol condensation, you need 2 alpha hydrogens. If you only have 1, you're stuck at the aldol. Okay?
Then the hydrogen on the other ring, does that become less acidic because we formed that alcohol?
So I'm going to guess you're saying now the green hydrogen?
Yeah.
Yeah, that green hydrogen is no longer acidic. Okay? It is the same as the purple one in effect, okay, as far as location goes, except the green one no longer has a carbonyl to do resonance with if we remove that hydrogen. So that green hydrogen is not acidic. Okay? The one underneath we'll go ahead and do in black. Okay? So since we addressed the issue in that first one, we need 2 alpha hydrogens. So before I even jump into this one, what am I going to look for? Alpha hydrogens. So there's my alpha position, and I have 2 alpha hydrogens, which means I can do the aldol and the condensation right after. This is where I can kind of get away with my cheat. Right, so I just drew my 2 molecules. What happens is the first step, is my eraser too big? It wasn't too bad. Is I link those, and I'd have that O minus. I still have an alpha hydrogen, so I can remove that alpha hydrogen and do the elimination, and I'd have the final product. Remember, just like the VIDIG, where we could stack the 2 reagents and just delete the oxygen? Same thing can happen here. Stack the 2 reagents, delete the oxygen, connect the carbons. You now have your answer. We've now done the aldol condensation. Of course, it's not going to look like that on the exam because that's now stacked. We want to try and stretch that out as long as possible so that it takes up less space on our page. Make sense? So we could then go through and count that out. This is where numbering can come in handy. 1, 2, 3, 4, 5. Looking at a 5-member chain, there's 2, 3, 4, 5. Position 1, I have my aldehyde. At position 2, I have the methyl, the double bond. Position 3 was the double bond, and then 4, 5, there it is. Say that again?
Where was the alpha on the hydrogen?
The alpha hydrogen came from position 2. Those were the hydrogens that we removed. To step 1, make it a nucleophile. Step 2, do the elimination. Okay. Other things we can do to check: how many carbons in our starting material? 3. How many carbons need to be in our product then? 6. Did I draw it right? 1, 2, 3, 4, 5, 6. Yep. Right. So we could count carbons to help us kind of evaluate that. The numbering of carbons will become very important in this to make sure you can match up your carbons correctly. Okay. The next one is a what? Okay, and I'm going to need to clear up some space. Why is that next one a what? What's going on with that? What's the problem with there? So we're going to hook and go up. What's that? 3 reactants. Okay, well, the base is going to react with the acidic hydrogen. Okay? In these 2 structures, the most acidic hydrogen is going to be an alpha hydrogen. Does the second structure have an alpha hydrogen? Nope, so I don't need to worry about it. Does the first structure have an alpha hydrogen? Yep, so what can happen is I will go through and make my nucleophile. Right, there's the nucleophile. That now needs to react with an electrophile. Where is there an electrophile? Carbonyl. I heard the right structure. Okay, so we could do our cheat method. I'm just going to draw a pH. Right? We were saying that was an electrophilic carbonyl. Everybody agree with that? What about the carbonyl on the other structure? Isn't that also an electrophile? Yeah. What does that mean happens? We get 2 products. Should I draw this right? Okay. Is this going to be a good reagent choice as our match? No, this is a bad setup because we're going to, at best, we're getting 50% yield. Okay, there might be some variation off of that because one electrophile is slightly more electrophilic than the other, right? But there isn't a huge difference between those. So I get 2 products. What happens when I hit WTF? We've got a base. What is the base going to react with? The acidic hydrogens, which will be our alpha hydrogens. Which alpha hydrogen? They both have alpha hydrogens, which means how many nucleophiles do we have? 2. How many electrophiles do we have? 2. We're going to get all possible combinations. That's why that's W2F. I don't even want to draw them. Okay? Every possible combination. Okay? You can get the nucleophile reacting with the same, the nucleophile reacting with the other electrophile. Okay? You can get nucleophile number 2 reacting with its same, or you can get it reacting with the other electrophile. You end up with 4 possible products. Okay? Horrible design. If the previous one was bad design because we had 2 products, that one's even worse. Okay? What happens when we move to the third reaction? What did we change? We added steps. Well, what are those steps going to do? Because when I did this one, the base could react with either one of those. By adding in this step, what happens? The base can now only react with the first one. So in theory, I only have 1 nucleophile and 1 electrophile. But what kind of base did I use? Just a strong base, not a stupidly strong base. Which means I deprotonate some of the hydrogens, but not every single one. Which means what else is floating around in solution if I do just step 1? The first structure can react with itself. It has both a nucleophile and an electrophile. So this pairing, by doing it step 1 and step 2, does limit some of the products. Right? But I should expect still at least 2 products. Right? Do I need to draw those 2? I'm going to take that as a no. Right? The last one has a star next to it, meaning you should have been able to do it. Why is that one now all of a sudden better than all the others? It is a stupidly strong base this time. Instead of using an ethoxide, I'm using sodium hydride. Sodium hydride now is going to react in entirety. There is no equilibrium now. That sodium hydride is going to react with what? The acidic hydrogen. And it's going to remove making the nucleophile in that very first step. Because it is such a strong base and there is no equilibrium, it is going to remove all of those acidic hydrogens. And it's going to do it fast enough that what doesn't happen?
Reacts with itself.
It can't react with itself. So we take our starting carbonyl and we convert it entirely into a nucleophile. Once it is now negative, that carbon of the carbonyl is no longer electrophilic. But it's still a carbonyl, isn't it? Why is that not electrophilic anymore? We have resonance to stabilize it that prevents that from acting as an electrophile. The only reason it could react as an electrophile before was because we used a not as strong base that only converted some of our carbonyl compound across. Does that make sense? Now that we've set it up with a stupidly strong base reacting with our first species with an alpha hydrogen, right, we can convert all of that into a nucleophile. We then move to the second step. Well, there's now no base. It's just nucleophile and electrophile. I get one product. I can greatly improve the yield or the expected yield out of my reactions by very carefully selecting which nucleophiles or when I generate nucleophiles and electrophiles. So if we drew out that structure again, we'll attempt the cheat on this. Is that high enough? It is high enough. Okay. We'll draw our other one, our electrophile underneath. We remove the oxygen and we continue our double bond through. Ooh, I did a condensation. Did I have 2 alpha hydrogens to allow for that? Yeah. So cool, that was fair game. I now have my final product and I only end up with 1. So when we move into the aldol condensation, there are these little kind of nuanced things that we have to watch out for. Okay, we have to know what happened, and then we have to be cognizant of what bases we're using along the way. We good with that? Okay, so our big lessons. We need alpha hydrogens. The very first one didn't have an alpha hydrogen. Yeah, that's not going to happen. We get nothing. Okay? Crossed aldols. So before we looked at those examples, we just had one aldehyde. And we said, well, what does that one aldehyde do under these conditions? Well, we now have crossed aldols. Well, crossed aldol just means we now have more than one aldehyde, right? Or more than one ketone, which we'll see in a second. Okay? It means we're mixing two different things. That's why it's crossed. We do have big, big issues with control. Okay? We could even look at it as a quality control for the amount of products that we can come out of it. Okay? So things that we want to control. Only one species should have alpha hydrogens. So we can control our reagents. Make sure that when we run it, we make sure that only one of them has alpha hydrogens. Only one of them can possibly be a nucleophile. Okay? So that can help us out. And or only one species should be allowed to enolize. Only one species should become an enolate. That's really our base control. So that's where we can bring in sodium hydride or LDA. Those are the two bases that we can use. Okay? Breaking it into two steps really maximizes the yield. Okay? The one where we only had one alpha hydrogen, that's pretty good, but we still have kind of the ability for our alpha hydrogen to self-react. Okay? We've limited side products, but we still have that issue. Okay? The last one completely limits everything. We can use a better base, right? And we limit when those reagents touch each other. Make sense? Okay. Are there other base issues that could pop up? Okay, so we take a look at the structure shown. Now, instead of looking at aldehydes, we're looking at a ketone. Okay, what is the issue with the ketone? Okay, we get steric hindrance. Yeah. What else shows up as an issue?
You have more alpha hydrogens.
Okay. We have a lot more choices for alpha hydrogens. If we go through and look at this structure, it sure looks like I've got 4, right? 1, 2, 3, 4 alpha hydrogens. Okay. Which means I have 4 potential nucleophiles. Which then means minimally I have 4 potential products. Okay. Can I simplify that? It's a mirror in this case, which means I only have 2. Okay, that helps out. So now I only have 2 alpha hydrogens. Okay. Well, are those alpha hydrogens different, red versus blue? Yeah, because, don't tell me red and blue. One is terminal and one is internal, and that's relevant because our enolate becomes kinetic versus thermodynamic. Okay, how do we control the kinetic or thermodynamic enolate? We can change our base from being strong to stupid strong. Okay, we could also change the temperature. Okay, so we need to be very cognizant of what base we're using as soon as we shift into a nucleophile, or as soon as we shift into ketones as our potential reagents. Okay? Those bases will dictate which position is the nucleophile, potentially. Okay? Does anybody else notice an issue or something interesting, particularly with that structure?
Attack itself.
What do you mean it can attack itself? Haven't they always been attacking itself?
Well, it can form the cyclic structure.
Okay. When we talked about attacking itself before, there was a second molecule to react with because we needed a second carbonyl. What is special about this molecule? There are 2 carbonyls. Those 2 carbonyls are in the same structure, which means I could enolize that red position or that red hydrogen, and I could have it attack like so. In what kind of a reaction? An intramolecular reaction, okay, or cyclization. Okay. When we did acid-base reactions, remember we had those acids and bases who were like, oh, I just want to have that hydrogen get pulled off the nitrogen by the oxygen up there. so that I have my good leaving group and the nitrogen stays. Remember that? I'm talking about nitrogens. And we want to do that intramolecular reaction. I said those were horrible. You can't do those. Why did I say you couldn't do them? Okay. It was not more than 6. It was less than 6 in the transition state. Okay. So that if we tried to do that acid-base reaction, we would have had to force the structure into a cyclobutane type structure. And that's not a stable ring structure, so it's not likely to happen. Okay. What's going to dictate whether we get the intramolecular reaction here? What type of ring structure does it produce when it reacts? So we got 2 possible products here. We could either have the red hydrogen come out or the blue hydrogen come out. And the blue hydrogen generates that enolate. Draw those 2 products. So there's the red product. Right, and you may look at it and go, that looks ugly. That's fine. Right, and officially not a red product yet. All I did was make that bond. Right, I'm not worried about the condensation yet. Okay. How did I go through and do that for those of you that were looking down? Okay. I would start at the bond that I'm trying to make. I'm trying to connect carbon 2 to carbon, in this case, what, 7? So there I can color code it. I know 7 is connected to 6. I know 6 is connected to 5. I know 5 is connected to 4. I know 3 is connected to 4. And 3 is connected to 2. Yeah? 2 is connected to 1. 2 is also connected to the carbonyl that was attacked. So I'll have that O minus. Okay. At position 6, oops, let's get rid of that 8. Position 6, I had the carbonyl. Everybody see that? So now I look at those 2 products and decide which of those is more likely to form. And yeah, I drew them all goofy, but that's when I would go back through now that I've got them drawn. And the red one, I've got 1, 2, 3, 4 atoms in my ring. I'm looking at a cyclobutane. Based on what I remember from first semester, cyclobutanes are not likely to form. I would probably put a line through that and check the next one. We got 1, 2, 3, 4, 5, 6. I'm looking at a cyclohexane. Cyclohexanes are incredibly stable. This is likely the structure I want to be working from. Now I can take that further. Okay. Do I still have alpha hydrogens? Yup. Which means I can continue this through the condensation, kick out my leaving group, and end up with the pi bond there between 1 and 6. Or that's 1 and 7, sorry. I don't know why I called that one. Oh, no, different numbering. 2 and 7. Make sense? So the cyclic structures can still happen, and everybody gets bogged down and confused behind them because what you're doing is trying to map everything beautifully out at the end. Do either of those look like a perfect square or a perfect cyclohexane? No. Do they get the answer across? Yes. Okay. Focus on getting the answer correct first, and then if it's a show your work and you've got to make it look pretty, okay, you don't, okay, but if for some reason you have to, then you can make it look pretty. But get the answer down first, then you can deal with it later. Okay. Make sense? Okay. So when we're doing these cyclizations, okay, they can happen, and you'll notice with the ketones, there are multiple potential cyclization results. We want to set it up or do the cyclization reaction that results in the most stable product. We're looking at 5 or 6 membered rings. Okay. When we're doing these, it's typically a choice between a 4-membered ring and a 6-membered ring because of the spacing around the carbonyl. Okay? Make sense? Okay. Here we run into some fun part. What happens if we do conjugate addition? Come back to haunt us. Bite us again. Okay? Notice down in that bottom reagent number 2, okay, that is now a conjugate or an alpha-beta unsaturated carbonyl compound, as we talked about at the end of the last unit with our Gilman reagents. Okay? With the Gilman, they would attack the 4 position, okay, or attack the alkene, if you will, and we'd end up with the 1,4 addition. The Grignards attacked and gave us our 1,2. Okay, and it was all about the strength of the negative. The Grignard were stupidly negative. The Gilman were only partially negative. Well, enolates are a little bit worse than kind of in the middle. They're like dead smack dab in the middle. If we take an enolate, it can go either direction. You get both products. Gilman at least does 1,4. Grignard does 1,2. Gilman does everything. Or sorry, enolates do everything. So you get a giant cluster F of a mess. Okay? Which is why we typically don't look at single enolate forms. If we go through and take a look at the bottom reaction, okay, we have our alpha beta unsaturated carbonyl, which needs to react as what? Not to color code hints. What did our alpha beta unsaturated carbonyl act as? An electrophile. Our Grignards were negative. Okay, our alpha beta unsaturated is our electrophile. Okay, because remember, we're looking for our carbon nucleophiles. So we add that strong base to remove an alpha hydrogen, and we'd have an enolate, right? Okay, and didn't I just say we don't react enolates under these circumstances because we get too many products? And yet, this reaction is very clearly showing only one product. Am I a liar? Probably, but not now.
It's the most acidic hydrogen, alpha hydrogen.
What is special about that alpha hydrogen? Yeah, it's the most acidic. It's still forming an enolate, right? And I said we don't do these reactions with enolates.
It's the resonance
It's the resonance. What resonance?
between pi bonds to the carbonyl pi bonds and the electrons there.
That's an enolate. I agree, yeah, that resonance, that's totally an enolate. And I said we don't do enolates. It's not one enolate, it's 2 enolates. It is doubly resonance stabilized. Okay? By being doubly resonance stabilized, I have now weakened the negative, making it more like which of our G's? The Gilman is less negative, the Grignard is more negative. That double resonance stabilizes it. They literally give both products, both the 1,2 and the 1,4. It's a mess of products, we don't want to deal with it. Okay? But if I still have that functionality or need that chemistry, I can go through and do it. And I'll do it by bringing in 2 enolates with air quotes. Okay? Those of you in lab, this should look really familiar because we did it. This is the lab. Okay? In fact, this almost very reaction is what we do, if not this very reaction, is what we do in lab, or what we've tested in lab. Okay? So our enolates are nucleophiles. They're great. As soon as we bring in the 1,4, we have to be thinking about this conjugate addition issue. Because that electrophile has 2 electrophilic sites, we have to watch both. Kind of make sense? Okay. So, why does it all of a sudden get its own name? I have no clue, but it does. When an enolate attacks the beta carbon, right, which is another way of saying the enolate attacks the 4 position, okay, or in a 1,4 addition type situation, that reaction is known as a Michael addition. Okay, yeah, that's it. That's literally it. So if we go through and take a look at the table here, what they're trying to show is a variety of Michael donors. You mean nucleophiles? You mean enolates? Yes, that's exactly what they mean. Okay. So look, we have the double resonance. Double resonance. Okay. I'll deal with the rest in a second. And then Michael acceptors. Oh, you mean a 1,4 or an alpha beta unsaturated? Let's number that right. If I'm going to yell about them coming up with stupid stuff, I shouldn't do it. An alpha beta unsaturated carbonyl, or an alpha, connect. Or another alpha beta unsaturated carbonyl, or another alpha beta unsaturated carbonyl. Yes, yes, I mean exactly like that. Okay? Just because they come up with a new name doesn't mean anything changes. The chemistry is still the same. Okay? Where might we pause with that thought behind some of these? Let's take a look at this guy. We said we needed 2 resonance. I only see 1 carbonyl. I only see 1 enolate. Damn it, Mike, you lied again. Shaking your head. Yeah, you did. There's resonance with the nitrile. We still have polar pi bonds out there on the nitrile. That is a double resonant structure. Okay? If we move down to the last one, oh, Mike, there's no enolate there. Yeah, I know, because that's the Gilman reagent, which does 1,4 addition. Okay? The Gilman reagent gets labeled twice. One as a Gilman reagent, and then the second as a Michael donor. We're naming named reactions. Anybody else see that as kind of stupid? Just for the record. What about this last one? I don't see a carbonyl over there, so there's no resonance. But there's not a carbonyl there either. What's going on? When in doubt, draw it out. What is the Lewis structure for nitrate? Is there effectively a carbonyl out that direction? Yes. But there's only one. And I said we don't do it with only one. What is special about that one? Yeah, there's resonance within itself. Does the nitrogen ever become not positive? If we draw out that resonance result, what happens? We put the double bond up to the nitrogen. Cool, so now the nitrogen has gained electrons, so it should be okay, right? But if we go through and calculate it, notice the nitrogen is still formally positive. Okay? The nitro group is such a strong electron withdrawing group that it will make that hydrogen exceptionally acidic, and now that conjugate base stable enough that it acts as a Michael donor, as a enolate type structure. Make sense? How about on the right hand side? Do we see any over there that look kind of weird? I said we needed alpha beta unsaturated carbonyl. All right, well, this one's still alpha beta, isn't it? There's the carbonyl. Well, this is alpha beta for unsaturated, but it's not a carbonyl. It's because it doesn't have to be a carbonyl, it just needs to be a polar pi bond. There is a polar pi bond with that nitrile. How about the next one? That's alpha beta. I don't see any pi bonds. When in doubt, draw it out. And what do we have out here? We have that polar pi bond. Okay, kind of makes sense? So look for your balances of charges, look where those electrons are flowing, and kind of build from there. Okay? Do you guys want to provide the mechanism in the product, or are you okay with that? Well, I'm going to take that as okay. We'll come back and do that if we get time. Enamines, super useful for conjugate addition reactions. Anybody remember the enamine? Well, we didn't talk about those. Yeah, we did. When nitrogen was a nucleophile. With nitrogen as a nucleophile, what happened? Nitrogen is a stronger electron donor than, say, the oxygen. So as long as I'm in an environment where I have the majority of nitrogen and a minority of oxygen, I'm removing, that says removing, oxygen from the solution, I can go through and replace the oxygen with the nitrogen. Okay? We did this as kind of an imine. What is the problem with that structure as shown? Excuse me. And in case you want to call me out, I didn't show a ring. You should be able to look at that and be, that's the problem. What's the problem?
Positive nitrogen.
That nitrogen is positively charged. Does nitrogen want to be positively charged? No, so what does it do? Steals the electrons from the carbon. Does carbon want to carry a positive? No, what does it do? It steals electrons from a hydrogen to make the enamine. Okay? It's not just an alkene because there's a nitrogen connected to one of the carbons of that, so it's an enamine. Okay? How would we predict this one to act? 1,2 or 1,4? It's going to be a 1,4. Okay. The nitrogen being less electronegative, I can share the electrons in, weakening that negative a little bit, making it more like a 1,4 than like a 1,2. Okay. What else could we do behind this structure? Okay, so enamines have this further benefit. That can favor the kinetic enol. If we take a look at our enamine that's shown, do you see kinetic or thermodynamic? Trick question. It's a trick question because we're trying to form effectively the enol, so in quotes, our enamine. We're either placing the pi bond on the right-hand side or we'd be placing it on the left-hand side. What is the difference between those products? They're the exact same thing. There is no kinetic or thermodynamic. To decide kinetic versus thermodynamic, what do I need to do? Change the structure. If I added a methyl group, now would I have a kinetic versus a thermodynamic? Yes. Okay, now there's a clear distinction between those. Okay. Interestingly enough, when we do the nitrogen enamine, we favor the kinetic, okay, which I guess I've been coloring in blue. We actually get very little to none of the thermodynamic. That one doesn't happen. Okay. If we'd started with the carbonyl, both would have been nucleophiles. I would have had two sets of products coming out because we now have two nucleophiles. If I converted across to the enamine, okay, I now only get one active nucleophile. That's kind of neat. But of course then, why? Might help if we drew out some structures here. Let's go through and make that a nitrogen. Why would I favor the kinetic over the thermodynamic? It's a really hard one to see.
Steric hindrance. Yeah, attacking the hydrogen.
It's actually a steric hindrance of the atoms connected to the nitrogen and the methyl group. Those two butt up against each other. How would you see that? Everybody's favorite, Newman projections. Yay! Okay. There's a strong steric hindrance that prevents the elimination that direction. Okay. Because of that steric hindrance, I can't get the thermodynamic, which means I only get the kinetic. If there's an oxygen out there, it can't have any more bonds. There is no steric effect. So now I get both the kinetic and the thermodynamic as possible products coming out of that, which means I get two potential nucleophiles. The enamine cleans that up a little bit, okay, by preventing the thermodynamic nucleophile from forming. Okay. Kind of neat. More directly relevant for those of you, say, in lab, because that needs to go into your lab report. Yay! Okay. So, conjugate additions, they do 1,4. What if I want my carbonyl back? Okay, well, remember, nitrogen and oxygen are strictly equilibrium reagents. If I want the oxygen back, I can reverse it by adding in a ton of the oxygen source. The ton of the oxygen source would be water, and then I can try and remove the nitrogen source, and I can get my carbonyl back. Okay, kind of makes sense? Okay. So we could go through and do the reagents necessary to, yeah, we'll do that as another example on Wednesday. Okay. Robinson annulation, yet another name to this. What happens? Well, what am I starting with? Starting with base and an alpha hydrogen. I can make a nucleophile through an acid-base reaction. Then I have an alpha-beta unsaturated carbonyl. So I can take my alpha-beta unsaturated carbonyl with my nucleophile and do what kind of reaction? In addition, in the 1,4, come on, pen, 1,4 chemistry. Okay. Now I've got that as my final product there. And this is one of those other weird ones that are like, oh, let's just do this because this would be cool. And then they didn't get that. Okay, what happened in the next step? Okay, an aldol condensation. Why? That black product has what in it? It has a carbonyl that's indirectly useful. It has alpha hydrogens. So I can run an acid-base reaction again to give me a nucleophile. What can that nucleophile then do? It can react with the electrophile of my carbonyl in a nucleophilic addition. Thank you for adding that information. To give me what kind of a product? As a hint, it ends or starts with A and it ends with L. The aldol. I don't have an aldol product. What happens? The condensation, which is what type of reaction? An elimination. What did I eliminate from the structure? Water. Okay, so we did a nucleophilic elimination to get us our final aldol condensation product. By stringing all of those reactions together in that order, we end up with now a Robinson annulation. So we took several named reactions, combined them with a bunch of non-named reactions to get another named reaction. It's like a bad game of Pokemon or something. At least that's what I'm envisioning in my head. Okay. With that, we'll have to go ahead and stop. We will start Wednesday with pretty much all those example slides. So providing mechanisms and products for, it looks like an aldol or a Michael reaction, then a conjugate addition, and then, well, actually, yeah, we'll also look at this one. This one, whoops. Just to give you a heads up, this one here, I will make a quiz. Okay, so if you want to go through and work that and make sure you understand how to do it, that's probably a good idea. I will make that an official quiz, but we'll do the other ones as practice. For next class, for Wednesday next class. Okay, and I'll give you time to work on it in class too, but I would prefer if you did it at home, okay, or even in office hours to get that nailed down. Okay, after that.